Hello everyone, welcome back to today's session. Myself, I am Santosh, lecturer in Electronics and Communication Engineering Department, Government Polytechnic, Karkala. So in the last session, we have discussed multiple register transfer, LDM and STM instructions. And also we have discussed different addressing mode for LDM and STM instructions. So in this session, I am going to explain stack operations. So stack operations using STM and LDM instructions. So here also the addressing methods for stack operation. What are the different addressing modes for stack operation? There's one more instruction called swap instruction. For each instruction, I will give one example for each instruction. At the end of the session, you will be having multiple choice questions. So before going to the actual topic, I will first explain few basic concepts related to stack. So you already studied in 8051 microcontroller. A stack is a part of memory arranged in last in first out or first in last out manner. So LIFO or FILO manner. So last in first out or first in last out manner. So that is the basic principle of the stack. So it is used to store address and data while a subprogram or ISR, so interrupt service routine, is executing. The stack pointer is used to access the stack memory. So here we require one pointer register, that is a stack pointer SP. It is used to access the stack memory. So the memory location where a byte was most recently stored is called the top of the stack. So normally SP register that points to the top of the stack. See, in 8051 microcontroller you have already studied. So what is push and pop operation? Push and pop operation. So pop means retrieving the data from the stack or removing the data from the stack. So push means placing data onto the stack, store or save the data onto the stack memory. So during the push, it save the data onto the stack first, then SP is incremented by 1. So during the pop operation, it retrieve the data from the stack memory first, then SP is decremented by 1. So this is in 8051 microcontroller. So to implement stack data structure, few things are required. The first one is obviously the memory. So without memory we cannot implement stack. So an area of memory. So an area of memory to store the data. So next is to access the stack memory. So we require SP. So that is the stack pointer. The stack pointer register is used to point the top of the stack. Then the stack growth convention. It may be ascending or descending stack. So in ARM architecture we are not having any dedicated stack memory, but with the help of the instruction or software programming, so we can implement this stack memory. Okay, so first we will understand few basic concepts related to the stack operation. So we are having different types of stack operations. So first one is the ascending stack. So ascending stack grows in the upper direction. So it starts from a lowest memory address, and as data items are pushed onto it, progresses to higher memory address. So ascending stack means from lower address to higher address. So it is growing up. So lower address to higher address, whereas in descending stack, descending stack grows downward. So downward. So if it start from a higher memory address to towards, as the items are pushed onto it, process to lower memory address, from higher memory location to lower memory location, whereas in ascending, lower memory location to higher memory location. So then what is full stack? So stack pointer points to an address that is the last used or first or full location. So that is the stack pointer points to the last item onto the stack. Whereas in empty stack E, the stack pointer points to an address that is the first unused or empty location. That is, it points to after the last item onto the stack. So I will just summarize all these stack operation here. So first consider full ascending. So these are the memory address. Here I have pushed 3 bytes of data onto the stack memory. So in full ascending, so what is ascending? The address is in increasing order. So from lower memory address to higher memory address. So see the direction. So where stack pointer is pointing, full means, so the stack pointer points to the last item on the stack. So stack memory starts from lower address, say from 0 to, so after pushing A, it will increment by 1. So B, after pushing B, it will come here. Then the stack pointer is pointing to last item on the stack. So this is called full stack. So whereas in full descending, I will take same memory locations. So here the stack grows from higher memory address to lower memory address. So that is in decreasing order. But the stack pointer pointing to, again this is the full. So full means the SP points to the last item on the stack. See here, this is the starting address of the stack memory. So this is grow towards the lower memory address. This is the last item on the stack. So now SP is pointing to last item on the stack. So this is the full stack. So whereas in empty ascending, so I'll consider same memory location. So ascending means again from lower address to towards higher address. It is in increasing order, but the stack pointer is pointing to the last item. The last item after the last item on the stack. So 0C is the last item, but SP is pointing to the next location, that is the empty location, free location. So this is called empty location. So now SP is pointing to next empty location after the last item onto the stack. So whereas in empty descending, so consider the same memory location. So descending means, so address, so going towards lower memory address, higher memory to lower memory address. So now the stack pointer is pointing to empty location. So that is the last item, next address of the next item after the last item. So here, so see the difference. So full ascending, full descending, empty ascending and empty descending. Ascending means lower address to higher address. The stack growth from lower address to higher address. Descending means higher address to lower address. Whereas in full stack means the SP points to the last item on the stack. See here, whether it is full ascending or full descending. Full means the SP points to the last item on the stack. Whereas in empty stack, it points to after the last item onto the stack. So here this is the last item, so next location it points to the after the last item onto the stack, that is the empty location. So this is the last item. Now SP is pointing to next memory location, so that is the empty location. So these are the important concept you should understand before going to the stack instruction in the ARM. So next, consider what are the different addressing methods or modes for stack operations. So as I told, ARM does not support any hardware stack. So software stack can be implemented using the LDM and STM instruction. LDM and STM instructions. So these are software instructions. So for stack operation, the base register is usually the SP, stack pointer. So So that is the R13 register, R13 or SP register. So there are 4 addressing modes available for the stack operations: FA, FD, EA, ED. So what is FA? So FA means full ascending. So now you know what is meaning of the full, what is the meaning of ascending. FT means full descending. EA means empty ascending. So ED means empty descending. So FA, FD, EA and ED. So full ascending, full descending, empty ascending, empty descending. So this is the pop operation. These are the pop operation. So LDM. So here, so we are using LDM and STM instruction for the stack operation. Instead of push instruction and pop instruction, here we are using LDM and STM. Why LDM and STM? So you know what is the meaning of LDM? So LDM means load memory. So load memory means it load the data or transfer the data from memory to register. Memory to register. So whereas in STM, so store multiple register. So store means you transfer the data from register to memory. Okay. So memory to register. So during the pop operation, what will happen? So pop means it retrieve the data from stack memory. So this is the memory now, stack memory. From it retrieve the data from stack memory. So LDM performs pop operation. So whereas STM store multiple. So store means register to memory. So push operation. So this is the pop operation and this is the push operation. So push means it saves or store the data onto the stack memory. See here the data is pushing onto the stack memory. So instead of push we are using STM instruction. See here pop operation, it retrieving the data from the memory. So for pop operation we are using LDM instruction. So that is the topic, today's topic. So stack operation, that is the push and pop operation using LDM and STM instructions. So here the LDM, so for pop operation, so we are using LDM instruction. So LDM. So we need to specify the addressing mode. So here the FA, so FA, LDM FA, FT, LDM FT, EA, LDM EA, LDM ED. So these instruction which is equivalent to LDM instruction. So LDM FA which is equal to LDM DB. So LDM FT means which is equal to LDM IA. So LDM EA which is equivalent to LDM DB. So LDM ED which is equivalent to LDM IB. So LDM DA means load multiple register. DA means decrement address by 4 after each load. So here increment address by 4 after each load. So here decrement address by 4 before each load. So here decrement address by 4 before, sorry, increment address by 4 before each load. So this is the push operation. So push operation means, so here you are using STM. So we need to use the same addressing mode. So if you use FA here during the pop, for push also you should use FA. If you use FD, so here also FD. So if you use EA here, so EA in push also. So your LDM ED during the pop operation. So during the push STM ED. So instead of we can write STM FA, so we can write STM IB. So store multiple register IB. So increment address by 4 before store. So here STM DB means decrement address by 4 before store. So here increment address by 4 after each store. So here decrement address by 4 after each store. See here, so I will explain one instruction here. So what is meaning by, so store means, so register to memory, that is the push operation. It is save or store the data onto the stack memory. So STMFA, so A means ascending order. So ascending order means lower address to higher address, from lower address to higher address. So where is the F means full stack. So where is the full stack pointer points to the last item onto the stack. So consider STMIB. So what is meaning of STMIB? Again store. IB means increment address by 4. So here increment means from lower address to higher address, right? So increment address by 4 before each store. So before each store. So full ascending, which is equivalent to IB, increment before. So similarly FD, so full descending. So descending means, so reverse. So higher address to lower address. Full means the same, the full stack means stack pointer points to the last item on the stack. So whereas in DB, so decrement, so see here decrement address by 4 before each store. See, both are same. So instead of STMFT, so we can use STMDB also. So these are the 4 pop instruction, push instructions, and the second column, this is the equivalent LDM instruction along with the LDM addressing mode for the pop operation, and this column indicates the equivalent STM instruction for the push operation. So now consider one example. So for push operation, so we are using STM instruction. So STMFD. So as I told already, the base register should be SPR R13. So here we are accessing the stack memory. To access the stack memory, we should use only SP instead of R1, R0, R2 or any other register. So we should use only the R13 or SP register here. So and we are using here two register R1 and R4. So STM, so store, the push operation means it pushing the data onto the stack memory. So let us consider before execution, these are the initial values. So R1 contains 2, R4 contains 3, and stack pointer contains the address 80014. So now the stack pointer is pointing to 80014. So okay, see here full means the SP points to the last item onto the stack. It is descending order. So FD, so full descending, so descending order from higher memory location to lower memory location. So what will happen after executing this instruction? So as I told already, which is equivalent to STMDB SP comma in flower bracket R1 comma R4. So which is equivalent to this instruction. So store means register to memory. So decrement address by 4 before store. So first it will perform decrement, then it will store the data. So now SP is pointing to 80014. So it will decrement by 4. So it will decrement by 4, then save the data. So which data will come here? R4 data is pushed onto the stack memory. Again it will decrement by 4. So now SP is pointing this memory location 800C. Now the R1 data will push onto the this memory location. So 3, 2. So again, so here R4 is pushed first, then R1 is pushed later. So because, so last session I have explained, for the lower memory address, lower number register will come. So for higher address, higher number register data will come. So here 800C is the lowest memory. So R1 data pushed here. So So 80010, this is the highest memory address. So here R4 data pushed here. So again here we have used exclamation symbols. It will update the end address to the stack pointer. Now the stack pointer address is 800C here. So after execution this instruction, these two data, so here R1 comma R4, I have not mentioned R1 dash 4, so don't confuse here. So if I return R1 dash 4, then R1 comma R2 comma R3 comma R4, 4 register. See here we have mentioned comma, so R1 comma R4, only 2 register R1 and R4 will pushed onto the stack memory using FT addressing mode. So STM FT, so which is equivalent to STM DB instruction. So consider next example, STM ED. So STM ED, again the base register should be stack pointer. So R1 or 4 data to be pushed onto the stack memory, which is equivalent to STMDA. So SP comma R1 comma R4. So let us consider before execution the initial values are, so R1 contains 0, 2, R4 contains 3 and stack pointer contains 80010. So now the stack pointer pointing to 80010. See here we have used ED. So E means empty stack. What is the meaning of empty? It's the stack pointer points to the location that is the after the last item. See here 14, so 02 is the last item, so it points to the after the last item on the stack, that is the empty location. See here empty, so now it is pointing to empty location. So in descending order, so D means descending stack, so which is equivalent to STMDA instruction. So DA means decrement address by 4 after store. So here it will perform store operation first, then after that it will decrement the address by 4. So it will decrement the address by 4. So now the stack pointer is pointing here, so 80010. So for what will it do? It will do first store operation. So it will store the data, so R4 onto this memory empty location. See here, so before execution this location is empty, now this filled with the R4 data. So later it will decrement by 4, so decrement by 4. Now the SP is pointing to next location 800C, so there it will push the R1 data, so 2. So here we have only 2 register, so 2 data, R1 register data and R4 register data pushed onto the stack memory locations. After the store or save, the SP is increment by 4. So now the SP is pointing to 80004. So now also this is empty location. There is no data inside this memory location. So E. So before execution and after execution, the stack pointer always pointing to empty location. Okay, so again here we have mentioned exclamation symbol. The end address will be updated to SP. So here SP contains 80008. So if this symbol is not present, then SP is unchanged. It will contain only the 80010. So let us consider LDM. So pop operation. So LDM FT. So LDM FT. So again base register is SP. So R1 matte and R4. So FT means full descending. So full means the stack pointer points to the last item onto the stack. So descending. So which is equivalent to instruction LDM IA. So LDM FT instruction is which is equivalent to LDM IA. So let us consider the initial values before execution. So now LDM means load multiple register. Load means memory to register. So memory to register. That is nothing but pop operation. So it retrieve the data from stack memory. So stack memory to register. So initial values are the register before execution. Register values are initially 0, and the stack pointer address is 800C. So now SP is pointing to 800C. So in that memory location 2 is present. In 80010 3 is present. In 80014 2 is present. 80018 1 is present. So these are the initial values before executing LDM FT instruction. So what will happen after execution this instruction? So which is equivalent to LDM IA. So what is IA? Increment address by 4 after load. So first it will perform increment address by 4 after load. First it will perform load operation, then it will increment the address by 4. So it will increment the address by 4. So here the SP is pointing to 8000C. So here we have used full memory location, right? So SP is pointing here 800C. So after first it will load the data. So it will load from memory to register. So this data is moved to R1. So pop operation. So it retrieve the data from top of the stack to R1. So later it will increment by 4. So now SP is pointing here. So this here SP is pointing here. So after retrieving data, so this location is empty, right? So now SP is pointing here. So first load, then increment address by 4. So again there is one more register is present in the instruction. So this data is moved to R4 register. So 3 is retrieved to R4 register. So later the SP is increment by 4. So only 2 register. So 2 times retrieve the data and 2 times SP is incremented by 4. Now after execution the SP is pointing here. So these 2 location now it becomes empty. So because we have retrieved the data from 800C and 80010. So these 2 locations are empty now. So now the SP is pointing to 80014. So F, that is called full stack. So full stack means SP points to the last item on the stack. So here before execution this is the last item. So SP pointing to last item onto the stack. After execution now this is the last item. So already we have retrieved the 2 data from the stack memory. Now the SP is pointing here. This is the last item on the stack at the present now. So next example. So LDM ED, so which is equivalent to LDM IB. So again pop operation means stack memory to register. Load means memory to register. So let us consider the initial values. So R1 initially 0, R4 initially 0. The stack pointer contains address 80008. So now the stack pointer pointing to address 8008. So here we have taken ED addressing mode. So empty. So empty location. So now the SP is pointing to empty location. So what will happen after execution? LDM ED or LDM IB. So LDM IB. So means IB means increment address by 4 before load. So first it will increment the address by 4, then it will load. So now the SP is pointing to 8008. The SP is increment by 4. First it will increment by 4, then load. So load means memory to register. So this data is moved to R1 register. So again SP is increment by 4. The now stack pointer is pointing to 80010 location. The second data is moved to R4 register. So only we have mentioned 2 registers. So that is the end of the LDM IB or LDM ED instruction. So at the end, the stack pointer will be updated with the end address. Now the SP is pointing here. So this SP is pointing here. The now SP contains address 80010. So before execution it was 8008, now 80010. So after retrieving these two data, so now the stack, this location becomes empty. So now the SP is pointing to empty location only. So before execution also, after execution also. So ED means empty location. So before execution SP is pointing this empty location. So after execution SP is pointing to this empty location. So similarly, so try for other addressing mode also. So I have taken only 4 example here. So for remaining 4 examples, for remaining 4 instruction, you try by yourself. So next is the swap instruction. So what is swap? A swap instruction is a special case of a load store instruction. So it swaps the content of memory with the content of a register. So in 8051 microcontroller, so you have studied swap instruction also. So there you have studied swap A. So swap accumulator. So before execution, suppose if the accumulator contains 25H, so after execution it will becomes 52H. So swap A means swap or exchange the accumulator content. So lower nibble with the higher nibble and higher nibble with the lower nibble. So before execution 25, after execution 52. So here also swap instruction is there. So it is a special case of a load store instruction. So it swaps the content of memory with the content of a register. And this instruction is an atomic operation. So it reads and writes a location in the same bus operation. So that is the meaning. So preventing any other instruction from reading or writing to that location until it completes. So until the completion of this swap instruction, it prevents any other instruction for reading or writing to that location. So until it completes the swap instruction. So now consider the syntax of swap instruction. So swap instruction is SWP. So B means byte. So this is also conditionally executed. So this is optional. So RD RM within square bracket RN. So this is the memory location. So where RD and RM contains the data. So here that register contains the memory address. So swap means a swap, a word between memory and a register. So see the direction. So from memory whose address is held by Rn, that will move to RD register. The register value Rm, it will move to memory location through Rn register. So swap a word means 32-bit data from memory will move to RD and 32-bit data from RM to Rn. See here. So 32-bit data from memory whose address held by Rn will move to, so initially it will move to some temporary register, temporary location. So then the RM value, so will move to that memory location. So later the temporary value will move to RD, which is nothing but the moving the data from memory to RD. So see here, so memory to RD and RM register to memory location. So whereas in SWP B, so B means byte. So swap a byte between memory and a register. So here 8-bit data from memory is moved to RD and 8-bit data from RM is moved to memory location. So same thing, first it will copy to some temporary location, RM to memory location. The temporary value will move to RD register. So let us consider an example. So SWP R0, R1, in square bracket R2. So R2 contains the memory address. See here. So direction, so from memory location to register, R0 register, from R1 to memory location. See, memory location to R2, then memory location to, sorry, R1 to memory location, and R1 is unchanged. So let us consider before execution the memory location. So 9000 that contains value 0x12345678. So 32-bit data, so it requires 4 memory locations. So we are mentioning only the starting address. So in 9078 is present, in 9001 56, in 9002 34, in 9003 12 will be there. So 9000, 9001, 9002 and 9003. So these 4 bytes will be stored. So in R0 initial value is 000, R1 contains 0x11112222, R2 contains 0x00009000. So after execution, what will happen? So from memory location whose address held by R2 will move to R0 register. So R2 contains 9000. So in 9000 contains 1, 2, 3, 4, 5, 6, 7, 8. So this data will move to R0 register. See here, R0 register. So memory location to R0 register. So before execution, R0 contains, initially it was 0. So now it contains the memory location value. So memory to register. So 0x12345678. So then the R1 content will move to memory location. So R1 content. So 0x111222 will move to memory location. See here, 0x11112222. And R1 value is unchanged. So before execution and after execution, and also memory address R2, that also unchanged. So whereas in SWP-B, so swap a byte, so from memory location to register and register to memory location. So here only byte from memory and only byte from register will move. So here the 0 extended concept is used. So we have studied this in during LDRB instruction also, load byte. So load byte means from memory location to register, only 1 byte of data is transferred from memory to register, but register normally a 32-bit wide, so remaining 3 bytes of data will be 0 appended. The same thing also here will happen. So consider before execution the memory location 9000 contains 78, R0 contains 0x11111, R1 contains 0x4142, R2 contains 9000. So after the execution from memory to R0 whose address held by R2. So R2 contains 9000, that is the memory address. So from that memory location 78 will move to R0. So only 1 byte of data will move. So 78. The remaining digits will be 0 appended. See here. So before execution R0 contains 0x11111. So after execution only a byte of data from memory will move. The remaining digits 3 bytes will be 0 appended. So next, from register to memory, R1 register to memory, from R1 register to memory, but only 8-bit data, the lower 8-bit data 22 will move to 9000 location. R1 is unchanged, R2 also unchanged. So here only byte, swapping of the only byte, whereas in SWP swapping of the what, 32-bit data, here 8-bit data. So in this session, so we have discussed stack operation using STM and LDM instructions. So stack operation, which are nothing but push and pop operation. So using STM it performs push operation and LDM performs pop operation and swap instruction. And also we have discussed different addressing methods for the stack operations. So now let's look into a few multiple choice questions. 10 multiple choice question. Again, you take pen and paper, so write down the question number and write down the correct answer option. So, the first question, SWP instruction is used to A. Swap a word between memory and a register, B. Swap a byte between memory and a register, C. Swap a byte between memory and a memory, D. Swap a word between register and a register. So SWP instruction is used to, so SWP, there is no B here, so it is used to swap a word. So option A is the right answer. Swap a word between memory and a register. So second question, dash is the address that the computer acquires from the current instruction being executed. So A. simple address, B. complex address, C. non-effective address, D. effective address. So dash is the address that the computer acquires from the current instruction being executed. So the answer is option D, effective address. The effective address is the address that the computer acquires from the current instruction being executed. So third question, the LDMFT and STMFT instructions provide the dash and dash function respectively. So A. push comma push, B. push comma pop, C. pop comma push, D. pop comma pop. The LDMFT and STMFT instruction provide the dash and dash function respectively. So the answer is option C, pop and push. So LDM means load means memory to register, so it retrieve the data from memory. So pop. So STM means store the data onto the memory, that means the push operation. So LDM perform pop operation and STM performs push operation. So next question, STMFT, SP comma within flower bracket R1 comma R4, which is equivalent to dash. So A. STMIB SP comma flower within flower bracket R1 comma R4, B. STMDB SP comma within flower bracket R1 comma R4, C. STMIA SP comma within flower bracket R1 comma R4, D. STMDA SP comma within flower bracket R1 comma R4. So STMFT, which is equivalent to, so B. STMDB instruction. So next question, LDMFT SP comma within flower bracket R1 comma R4, which is equivalent to dash. So LDMFT, which is equivalent to A. LDMIB, or B. STMIB, C. LDMIA, D. STMIA. So the base register and the register are same. So LDMFT, which is equivalent to which instruction? So the answer is, so C. LDMIA. C, B and C, B and D, so STM. So these two are wrong. So from A, either A or C. So LDMIB or LDMIA. For LDMFT, which is equivalent to LDMIA. So C is the right answer. The next question, which of the following statements is true? A. Stack is either ascending or descending. B. Ascending stack grow towards higher memory address. C. Descending stack grow towards lower memory address. D. All of the above. So which of the following statements is true? The answer is D. So all of the above. So all statements are true. A stack either ascending or descending, right? Ascending stack grow towards higher memory address from lower memory to higher memory address, whereas in descending stack it grow towards lower memory address, higher memory to lower memory. So all of the above are right. So option D is the right answer. The next question, dash instruction used to carry out stack operations. A. Load, B. Store, C. Both, D. None of the above. Dash instruction used to carry out stack operation. So which instruction? Load, store, or both? D. None of the above. So answer is both. So load for pop operation, store for push operation. So stack operation means both push and pop. So for stack operation we are using both load and store instructions. So C is the right answer. So next question. So dash operation remove the data from the stack. So A pop, B push, C both A and B, D none of the above. So dash operation remove the data from the stack. So which operation? So answer is A. Yes, pop operation remove the data from the stack. So it retrieve the data or remove the data from the stack, pop operation. So next question. When you use a full stack, the SP, the stack pointer points to an address dash. A. The last used or full location. B. The first unused or empty location. C. Both A and B. D. None of the above. So when you use a full stack, the stack pointer points to an address. The answer is option A. So full stack means the stack pointer points to the last used or full location memory address. So it is pointing to last used data. So A is the right answer. So last question. Dash operation place the data onto the stack. So A pop, B push, C both A and B, D none of the above. So dash operation place the data onto the stack. So which operation? Yes, so option B, push operation place the data onto the stack. So pop, it retrieve the data from the stack, whereas push, it push the or store the data onto the stack. So this is the end of the multiple choice questions. So assessment by yourself. So so today we have discussed stack operation, push and pop operation using LDM and STM instructions, and also we have discussed different addressing modes supporting to stack operations, and also we have discussed swap instructions, swap word and swap byte. So I will end this session now. So in the next session I am going to discuss software interrupt instruction, PSR program status register instructions, and pseudo instruction for loading the constant, and NOP instructions in the next session. Thank you.